All right, so let's talk about how to build a bijection. This is lecture 3. A given function or map, it doesn't have to be bijection, right? But we could at least make it into a surjection, right? Which means that everything in the codomain is actually mapped to by something in the domain. Easy way to do that is just to replace the codomain with the range, right? In fact, a lot of times in like pre-calculus courses, we don't even talk about codomain, right? We just basically assume that the thing it's mapping to is the range, because otherwise the kids get confused. Actually, if you talk about sets, the kids get confused, but anyway. So anyway, certainly if we replace the codomain with the range, it's going to be an onto map. Now the question then is, how can we adjust F to be an injective map? So let's kind of drill down into that. What was a one-to-one map? F is injective or one-to-one if f of x1 equals to f of x2 implies x1 is equal to x2 for all pairs in the domain. All right. So what's another way to look at that? Well, we can look at the inverse image of a singleton. All right. And the inverse image of a singleton, y, set just containing y, is x in the domain such that f of x is equal to y. All right. So suppose that you had x1 and x2 in x for which f of x1 is y and f of x2 is y, right? Well, if that was the case, then that would mean that both x1 and x2 are in the inverse image of y. All right. This is also called the fiber of f over y, something like that. And so if we need x1 and x2 to be equal whenever, f of x1 and f of x2 are equal, implies x1 and x2 are equal, then certainly we're going to get into trouble if our inverse image of y has more than one point in it, right? Because we need x1 to be equal to x2. If x1 is not equal to x2, then it's not going to be one-to-one. So that's basically this theorem. A map is injective if for x and y, f function from x to y, we have the inverse image of y is either at the empty set, right? Which is to say that it's actually a point that's not in the range, all right? Or the inverse image of the singleton is just a single point. In other words, the inverse image of a singleton is a singleton, all right? For some x in the domain. And that has to happen for each y in the codomain. All right, it's either the inverse image of the singleton is either the empty set or it's a singleton. All right, in other words, an injective map is one for which every non-empty fiber is a singleton. All right. So a sort of a warm-up example here. Example 1. I almost always talk about this example as a point of habit. F of x equals to x squared. All right. So what happens if we look at f of x1 equal to x2? We get x1 squared equals to x2 squared. That solves to give x1 is equal to plus or minus x2. Oh, it's not one-to-one because we didn't get x1 equals to x2, right? So unless we limit the discourse to not allow the plus and minus solutions, we're kind of up a creek here as far as one-to-one. And of course, I already told you that the discourse was the whole real line there, right? So as we look at the inverse images of this map, we've got either the empty set for negative, right, because you can't have a negative number equal to x squared. We get just 0 if we're looking at the inverse image of 0, because only 0 squared is equal to 0. And for y positive, we get plus or minus the square root of y. Both of those map to y under the square map. Okay? So this function is not one-to-one, right? And it's also not a... this is not onto, right? Because it only maps to, what? Non-negative real numbers doesn't ever map to a negative number. So this function is neither one-to-one nor onto. But it is, of course, a popular function to talk about in pre-calculus. All right, so draw a picture of what I'm thinking about. So again, our goal is to think about how to build a bijection from a given map. Okay, and so. Here's a picture that kind of gives you the idea. Basically, we're mapping from x to y, all right? And we've got some function, right? It's going to cover the range of f, all right? So we know, first of all, we basically want to just cut off all this extra baggage over here and just cut the codomain down to the range. That will make it onto. Okay. Then over here, if our fibers are bigger than singletons, we're in trouble, right? Because then we've got a departure from one-to-oneness, a departure from injectivity. So we want the non-empty fibers, we want to replace each non-empty fiber with like just one point somehow, right? This, it's, you know, the fibers are simple though. Like there's a nice pattern here. It's not like you can have more than one fiber going through a point. All right, so these fibers actually partition the domain. The non-empty fibers partition the domain because membership in a fiber is an equivalence relation. x1 is equivalent to x2 if and only if f of x1 equals to f of x2. That actually defines an equivalence relation on x. And the fibers are actually the partition of this relation. I should say the non-empty fibers, right? In contrast over here, the inverse image of the part we cut off would just be the empty set. But all right, so point here, to obtain an injection, we need some method to select just one point from each of these non-empty fibers, all right? And like, so generally how to do that's an art, all right? It's like, I can't give you a general answer on how to do that. I would say usually people talk about taking a cross section or something like that. To be honest, there are people who've made their whole career in particular parts of math by coming up with a systematic but somewhat ad hoc method of taking a cross-section of a particular construction. Making that choice eliminates freedom, and it allows you to think things that you might not otherwise think, given more freedom. But anyway, let's look at an example that's based on my example one. I just want to show you how we can select something. Let's look at the fibers of the square map, all right? So here's a picture that hopefully makes sense. All right, so I took the number line and I bent it, all right? So under the square map, under f of x equals to x squared, the positive real numbers and the negative real numbers, they both map to the positive real numbers under the square map. And so 0 maps to 0, right? So if we look at the inverse image of a point over here in the range, all right, so I took the liberty of cutting the codomain from R back down to non-negative real numbers. That way I know it's onto, okay? So the inverse image of 0 is just 0. That's fine. That's already a singleton. But if y is positive, the inverse image of y under the original map f is got the plus and the minus square roots in it, right? So the fibers are not singletons, they're pairs. But how to select a point from each fiber, that's pretty simple. We just pick one of these, right? And so, you know, natural choice is just restrict to just the green piece. Green piece. Sorry. Green piece makes me laugh. Anyway, so square root of, oh, what have I done? Oh no, anyway. Square root of y from each fiber. We select the square root of y from each fiber to make an injection. F restricted to the non-negative real numbers is a mapping from, well, non-negative real numbers to non-negative real numbers. And in fact, this is a bijection. It is one-to-one and onto. So the trouble was our domain was too big. We just had to cut it down, get rid of half of the real line. And once we did that, we had singletons. Yay! Now, it's not always so simple, all right? So comment. The ad hoc method I just used in example 2, well, it is ad hoc, right? And generally speaking, as I was saying before, it's generally an art to figure out how to restrict the domain for a specific concrete example to actually make it into an injection. There are some general techniques, all right? But in terms of existence, the axiom of choice, as we'll discuss a little bit later in this lecture, indicates it's possible, at least in principle. Okay, so here's another example. Suppose you take the function from 3 by 3 matrices, all right, to three-dimensional space defined by just pick out the third column of the matrix, all right? I say that's clearly a surjection, right? Because you pick me any point in R3, and to show it's onto, you can just take the matrix, which is that point, put in each column, and it maps to there. All right, it's easy to see it's onto. Now, what's the inverse image of a particular point in R3? Well, it's the set of all matrices of the form M11, M12, M21, M22, M31, M32 with fixed A, B, and C in the third column. All right. So there are 1, 2, 3, 4, 5, 6 real parameters in this inverse image. This is clearly not a singleton, right? So what restriction should we place on R3 by 3 to make the intersection of this inverse image with S actually a singleton? You'll excuse me momentarily. I must ask my children to be quiet. Isaac, could we have less exuberant yelling, please? Thank you. Oh, Fortnite. All right. I don't even know why I bothered to tell him to be quieter. It's not in his DNA to be quiet. Let's see here. So anyway, so how can we make the inverse image of this this point, and how can we create a set S so that this intersection is a singleton? Well, I say there exist infinitely many choices, but certainly if we just set all of these guys to 0, that'll work, right? So I just say S is the set of matrices such that the first 2 columns are 0 is what I'm saying, really. So then F inverse of ABC intersect with S is that. Now that is a specific single matrix that is a singleton. So if I restrict this function to this set S, then we'll have an injection, and hence a bijection. So F restricted to this set S is a bijection. Now, it's interesting to sort of pause and smell the roses, so to speak here. Geometrically, 3 by 3 matrices form a 9-dimensional space in the sense of calculus 3. And the fibers are actually 6-dimensional slices. This set S, which we just constructed, is a 3-dimensional space which cuts through each fiber in just one point. So my picture on page 2, right, back here, I drew it as if the domain is 2-dimensional and as if the fibers were 1-dimensional, right? But it doesn't have to be like that. The fibers could be different dimensional. The fibers might not even have a well-defined dimension. What we do know is the fibers partition the domain. What I'm trying to say is, like, your fibers could be like, it could be 0-dimensional, they could be points in part of it, they could be lines in other parts of it, they could be circles, they just have to be, separate. They can't be overlapping because the fiber partition is a partition, a disjoint subsets, right? But anyway, so an example. And so, comment, confession, I suppose. I am covering Chapter 2, Sections 2.2, 2.3, 2.4, 2.5, and 2.6 rather lightly. It's good for you to read them in their entirety for your mathematical breadth, and I'll record a few high points here. So Chapter 2 is basically Minetti's chapter on foundations. He starts with induction, talks a little bit about properties of real numbers, and then he transitions to like foundational issues in foundations. And so I don't have a lot more to offer than he already has there at the moment, and it's kind of not the focus of this course, so I'm just going to kind of go through some things here right quick. Number 1, R is complete, and so the way to characterize that is that every non-empty subset of R that is bounded above has a least upper bound. I think I actually ended up using that in the next lecture in an example, weirdly enough. Let's see here. Lemma 2.3. This is actually before that, but I got it out of order. Sorry about that. Let X be a subset of the natural numbers, and let that be an infinite subset. Then there exists a strictly increasing bijection from N into X. In fact, if anything I'm shortchanging, there is a bunch of like technical lemmas about mappings from natural numbers into sets and how that relates to search activity and ordering and partial ordering, and all of those things may come back to bite us, but I'm just going to let that happen. When we need them later, we'll get back into those details as they come at us. I'm eager to get to the definition of topology and to start there. So anyway, another thing that's important for us to know about in terms of language is x and y are said to have the same cardinality if there exists a bijection f from x to y, and then we write cardinality of x equals to cardinality of y, or sometimes we'll just say the size of x equals to size of y. X is countably infinite if the size of x is the size of the natural numbers, and it's countable if x is either finite or countably infinite. Not everybody agrees on this terminology, so beware, but this is pretty common. I think that's the terminology I was taught when I took Foundations of Math a few years ago. Cantor's theorem is an important one. Cantor's theorem says that for x non-empty, there does not exist a surjective map f from x to the power set of x. Moreover, the size of x is not equal to the size of the power set, which of course begs the question, what do you mean power set? The power set. The power set is the set of all subsets. So P, funny looking P of x is A such that A is a subset of x. This is everything from the empty set all the way up to the set itself. This is the power set of x. All right. And another thing that I will forget, maybe this is evidence I'm not a true mathematician. I don't know. I think true mathematicians love this notation. X to the y is the set of all maps f from x to y. All right, so like in this example, the size of the real numbers is the size of the set of maps from the natural numbers to the natural numbers, all right? And that's the same as the set of maps from the real numbers to the natural numbers, right? And so I think this would actually be the set of real valued sequences. Is that right? No, wait a minute. No, other way around. Oops, sorry. And then this is the size of the power set of the natural numbers. So now, I believe the continuum hypothesis is that there's no other there's no other sized thing between the size of the natural numbers and the size of the real numbers, but I don't know if that actually came up in Minetti. I don't remember reading anything about that there. Maybe he gets to it later. I can't imagine a topology book not saying something about the continuum hypothesis somewhere. I don't think it was in his chapter 2. I was just looking at it anyway. All right, so if it's in there, my apologies. Shame on me. Okay, so two versions of the axiom of choice. Axiom of choice version 1. G from y to x is an onto map between sets. Then there exists a map f such that G of f of x is equal to x for all x in x. In other words, you can find a map which serves as like half of an inverse. All right, I forget if that's a left inverse or a right inverse of f, but I believe it's one or the other. But I have a bad habit of mislabeling left things right and right things left, so let's not even try. Excuse me. Again, this is one of those things that will get fixed when I finally teach Foundations of Proof again. So an equivalence relation on X is a relation, right? Which is a relation just means you can think of it as a subset of the Cartesian product of X with itself. And anyway, so if it's an equivalence relation, that means it's reflexive, symmetric, and transitive, which means X relates to X. For all x, it means that if x relates to y, then that implies y is related to x for all x and y and x. And transitive, of course, means if x is related to y and y is related to z, then that implies x is related to z, and that holds for all x, y, and z in x. So that's our equivalence relation. We need to know about that for sure. That's consistently something that will come up in mathematics, not just in this class, but in any upper level math class that pretty much as well in most upper level math classes. Anyway, so equivalence class is the set, this equivalence class with representative x. It's all y in big X such that y is related to x. You can talk about the quotient set, which is the set of equivalence classes. The quotient map maps x to its equivalence class, all right? And lemma 2.18 gives us a kind of nice result here, which is that if we have an equivalence relation on x and the projection, the quotient map, pi, and a mapping f, then the following are equivalent. The map is constant on equivalence classes, f of x equal to f of y whenever x is equivalent to y. And 2, there exists a unique mapping G from the set of equivalence classes to y, such that f is equal to G composed with pi. Here's a picture of it, so we can either do, let's see here, first shall come, how's it go? The first shall come last, so we go pi and then G, or we can go f either way to get from x to y. I don't know if it's entirely clear in the things I've written out here, but you know, replacing the domain with the, another way to attack the build the bijection problem would be instead of restricting the domain, to replace the domain with the quotient set, where we're modding by the fiber equivalence. See, that would also serve the purpose of creating a one-to-one map, right? Because if you think of everything in each fiber as a particular point, right, and that's the idea of the quotient set, right? It makes the whole equivalence class into a point. It squishes all the equivalent points into just one point in the quotient set, right? If you do that, that's kind of the same thing as just cutting through the set of fibers and picking one point out each. But the cost of working with the quotient set, of course, is you're no longer working with a subset of the domain, you're working with a new object altogether, right? The set of equivalence classes. So that's a conceptual cost to that approach, but it is, on the other hand, more natural than an ad hoc section of the domain. So that's another way we see throughout advanced mathematics that we find a way to create an injective map from a given map, right? That's really the heart of like the first isomorphism theorem in linear algebra, or of course in group theory, so forth. Now, last but not least, the axiom of choice version 2, it says that if you have a set and it is written as a union of other sets, all right, and this is a non-empty union, so this would be a, Well, yeah, I haven't even assumed that the sets are disjoint. I guess you don't need to. It's just the application I have in mind, the sets are disjoint, but this axiom doesn't require that. So you have a set of x is a union of xi for I in some index set. This doesn't have to be a finite index set, it could be infinite. Then there exists a map f from I to x, which is called the choice function, such that f of I is an element of xi for every I, right? So if you apply this to the case that the xi's are fibers, this axiom of choice means that you can always select, right? You can select a subset of the domain on which, if you restrict the function to that subset, you have an injection, right? Because it's just picking one point out of each fiber. This is the axiom of choice. When I think about axiom of choice, I think about this usually, right? And then finally, there's Zorn's lemma. It says let x, comma, less than or equal to be a non-empty ordered set. If every chain in x is upper bounded, then x contains maximal elements. So I would encourage you to read that. There will doubtless be something we need to use Zorn's lemma for later. We needed it in when I taught abstract algebra 2, it came up when we were looking at the interrelation between the unique factorization domains and principal ideal domains and Euclidean domains, and that discussion somewhere in there it come up. Remember, so it's a big gun, but it's relatively easy to understand, even if it's not. To me, it's not very intuitive. But if you find yourself needing to use Zorn's lemma, it's probably something pretty deep. Well, that's how I feel about it. I'm probably wrong, but anyway, I think that's it for this lecture. So sorry it's so short. I'll try to talk longer next time. Thanks, guys.